you see that this tangent plane is actually very, very nicely linearizing this nonlinear function. The linearization is occurring on this patch right here, which is a very small patch in the domain space. And this is actually the idea that we're going to use when we extend this idea not just to functions of 2 variables, but functions of 3 variables and any number of variables. That in our domain space, this what's called the linearization is the best linear approximation to the value of the function local to the point or around the point. And you can see the kind of combination of the actual contour curves or level curves of the function with the straight lines coming from this tangent plane linearization. And this is exactly the idea, which is if we kind of zoom in and make this little box here smaller and smaller and smaller, these lines coming from the linearization of the tangent plane are going to get closer and closer and closer to the actual contour levels of the function. I'll show this in a little bit when I introduce linearization. Before we do that, I want to introduce what's called the gradient vector, because this will be a very, very big tool for us going forward. So the gradient vector or the gradient vector field is what's called a vector field, or a collection of vectors at any given point. Remember that a vector at any given point is, you can think of it as like a directional arrow at any given point. But the idea behind the gradient field is that once the partial derivatives of a function are taken, we can store that information in a vector. This vector is called the gradient vector. And the gradient vector has the following notation. We use an upside down triangle to denote the gradient vector, and we put it to the left of the function that we're taking the gradient vector of. So for example, in 2D, where we have 2 partial derivatives with respect to, say, x and y, the gradient vector of a function f is just the collection of the x partial derivative and the y partial derivative. And if you've ever taken a linear algebra course, or maybe plan on taking a linear algebra course, there's a typical reason that we write this as what's called it's a 2-column, 1-row matrix, or a 1 by 2 matrix. But in 3D, the gradient vector is the collection of all three partial derivatives of the function. So it's the collection of the x partial derivative, the y partial derivative, and the z partial derivative. So in 2D, it's a function of two variables. In 3D, we're dealing with functions of three variables. You can do the gradient vector and the partial derivatives for any number of variables, for a function of any number of variables. But the reason that we call it a field is that at every given point we have a different value for the partial derivatives. So the partial derivatives in general are functions of position, of space. So the gradient is also a function of position. At any given point, this gradient vector is changing. So because of that, we call it a gradient field. So this collection of vectors has extreme physical significance for any given multivariable function, whether it's the multivariable function is describing temperature or height. One of the things that we'll prove eventually when we get to what's called the directional derivative is that at any given point, the gradient vector points in the direction of fastest increase of the function. So we will show when we get to the directional derivative that the gradient vector always points in the direction of maximum increase of the function f. So just going back to our examples to kind of show you what the gradient vector field looks like and why it's a field. Right, for example, 1, say, the derivatives that we calculated were 10x plus 4y. So the first component of the gradient vector is going to be 10x plus 4y. The second component of the gradient vector will be 4x plus 2y. This is a y partial derivative. So this is what the gradient vector looks like for the function from example 1. For example 2, we use g. The gradient of g will be the function negative 2x e to the negative x squared plus y squared, and negative 2y e to the negative x squared plus y squared, which we can simplify using some of our vector algebra from a previous calculus course. This is the same thing as the vector negative 2x, negative 2y, multiplied by the scalar function e to the negative x squared plus y squared. This is just a simpler way of writing this gradient. And then for example 3, look at the gradient of h. We found that this was 1 minus 2x squared times y times e to the negative x squared plus y squared, and 1 minus 2y squared times x times e to the negative x squared plus y squared, which is the same thing as 1 minus 2x squared times y, comma 1 minus 2 y squared times x, all of this times e to the negative x squared plus y squared. So these are the gradient vector fields for each one of these examples. And you can see why it's a vector field, because it depends on what point x, y you evaluate it at. It's changing at every different point that you evaluate it at. So I also wanted to point out that for example 3 here, in the preceding figures that you were shown of this function, specifically of the 2D density plot, level curve plot of this function with red and blue densities, I plotted arrows on the 2D plot, and those arrows were exactly the gradient vector field, so the gradient vector at each and every point in a sampling of points in 2D. So you can see that this gradient vector field has a lot of interesting properties if you look back to those plots. Specifically, the gradient vector field is always going to be pointing in the direction of maximal increase or fastest increase of the function at the point in which you have evaluated. So we're actually going to prove this using the directional derivative a little bit later on in the course. So what we want to do is define multivariable differentiability, what it means for a multivariable function to be differentiable. And it turns out that the existence of the partial derivatives is in fact not enough to define multivariable differentiability. And we'll see why in an example shortly. But in motivation for the definition of differentiability, we're going to go back to 1D and look at what it means for a function to be differentiable, or for the derivative to exist in 1D. And in general, this is, we'll call this differentiability of a multivariable function. So if we remember back to the definition of differentiability in 1D, a function is said to be differentiable at a given point. We'll say this point x naught, say. If the derivative of the function f at x naught, this limit as x goes to, or as delta x goes to 0, of f prime of x naught plus delta x minus f of x naught over delta x. Oops, gotta erase this right here. Let's if f at x naught plus delta x minus f of x naught over delta x, if this limit exists. And what this means is that the slope of the tangent line, or the linearization of our function, the best linear approximation of our function, is exactly this right here. It's the tangent line of the function, which is the function L of x or which is f prime at x naught. I'll actually start with f of x naught. It's f of x naught plus f prime at x naught times x minus x naught. So the tangent line, remember, of a function f at a point is exactly f of x naught, which is the y-intercept of that tangent line. Or sorry, the x naught intercept of that tangent line. It's exactly this. When x equals x naught here, right, the height of the function is f of x naught plus m times, so it's the slope of the function times x minus x naught. So the slope of this tangent line is exactly f prime. But if this limit exists, then this L of x is the best linear approximation to the function at the point. And what this basically means is that if you look very, very, very close to the point, so say you go to x naught plus delta for some delta, and x naught minus delta, so in a very, very small interval around this point, and think of delta as being very, very, very small here, the value of the function, the smaller delta gets, is closer and closer and closer to the value of the linearization, the tangent line. So for example, you can look at, we'll look at two separate examples from 1D, a function that is very, very nice and differentiable at every point. We'll look at f of x is equal to sine of x. And this is differentiable at every point, but we'll just look at the origin. So if you remember, sine of x looks like this. I think I can do better than that. So this point is negative pi over 2. This point is pi over 2. And if you look at the tangent line to this function, which we'll do in blue, just like above, the tangent line to this function is this line right here at this given point, the slope of which is given by the derivative f prime, which is just cosine of x at the point 0. F prime of 0 is cosine of 0, or 1. So the slope of this function at this point, the slope of the tangent line to this function at this point is 1. It's differentiable, and the closer you get to the function, the closer this tangent line approximates the function. So the tangent line, this tangent line is exactly given by L of x, which is f prime of x, x naught, plus the value times x minus x naught plus the value of the function at x naught. So it's going to be sine of 0 plus cosine of 0 times x minus 0, which is just 0 plus 1 times x minus 0, which is equal to x. And this is what allows us to say that for very small values of x, so when x is much, much less than 1, sine of x is approximately equal to x. This is where this approximation is coming from, and this is used very often in physics. But we can do stuff like this because the reason we can do stuff like this is because sine of x is a differentiable function at this point. So its linearization at any given point is approximately equal to the value of the function at the point. If instead you consider a different example, we'll use the standard example in most Calc 1 classes for a function that's not differentiable, and that's the absolute value function. We'll do that right here. This is I'll label this. This is a differentiable example. Our function that's not differentiable, we'll look at f of x is equal to the absolute value of x. Now remember that the absolute value of x looks like negative x for when x is negative, and it's the function positive x when x is positive. And you can show using the limit definition of the derivative that the limit from the left-hand side of that difference quotient or the limit as delta x goes to 0 from the positive side of the absolute value of 0 plus delta x minus the absolute value of 0 over delta x. The same thing as the limit as delta x goes to 0 from the positive of the absolute value of delta x over delta x. This limit is equal to 1. So this is saying that the derivative of this function from the derivative of this function on the left side, so the right side of the point x equals 0, x not equals 0, is 1. But if you do this exact same limit from the left-hand side, where the limit as delta x approaches 0 from the negative side, where delta x is negative, the derivative of this function, the limit for the derivative of this function is going to be the limit of 0 plus delta x minus the absolute value of 0 over delta x, which is the limit as delta x goes to 0 from the negative of the absolute value of delta x over delta x, which is equal to negative 1. So that's saying the slope of this function on the left-hand side of this function is negative 1. So this function is not differentiable at the origin, at x equals 0. And what that means is that there's no nice tangent approximation of this function. For any tangent line you try to draw here, or any linearization you try to draw here, the better you approximate the right-hand side with your linearization, the worse the approximation is going to get on the left-hand side, and vice versa. If you try and approximate the left-hand side with a given linearization, the approximation on the right-hand side is going to get horrible. So this is really what differentiability is. It's the lack of a linearization or a tangent, approximation to the function. So this is what it is in 1D, and this is the idea that we're going to have to take with us for multivariable functions as well. And with this idea in mind, it becomes possible to define the differentiability of a multivariable function. So just remember, this is an example right here of a function that's not differentiable. At x equals 0. This is an example of a function that is differentiable at x equals 0. So for multivariable functions, we say that we're going to do this for a function of 2 variables, but it can be directly extended to a function of 3 or 4 or any number of variables. We use an almost exactly similar condition. Say that a multivariable function is differentiable if there is a best linearization or linear approximation to the function. I should say here, a differentiable at a point R naught if there is a best linearization to the function at that point. For functions of 2 variables, this is the same as saying there exists a best tangent plane to the function that locally approximates the function, or you can define the tangent plane at a given point. So for a function of 2 variables, we say that, and we'll do this first, so 2D, the linearization is given by, we'll call it L of x comma y. This is the linearization of a function of x and y. L of xy is equal to the value of the function at the point x naught, y naught, or at r naught, plus df dx at r naught times x minus x naught plus df dy at r naught times y minus y naught. And we say this is a tangent plane because we can call this right here, say the z-intercept of a plane, this value right here, the slope of the plane in the x direction, and this right here, the slope of the plane in the y direction. And if we write down the equation, z is equal to the linearization at a given point, then z is equal to m times x minus x naught plus n times y minus y naught plus this b, or you can say z naught. You can use b if you want to use b, but I'm probably going to write z naught here because that's just relating it to the function f. And this is the equation of a plane centered at the point x naught, y naught, z naught. Or that this plane is exactly the tangent plane if these partial derivatives exist. So we can use this, and we'll see how to use this to define, an approximation of a function. If you say want to approximate a given function z, right? The value of a function, or the value of f for points that are very close to x naught, y naught, say, if a function is differentiable at a point, so this linearization exists and it's a good approximation around a point, if you kind of zoom in very close to the point x naught, y naught, so in this region right here, when you're like very, very close, say within delta, where delta is a very small value of the point x naught, y naught, then the value of the function inside this region, we'll call it D, is approximately equal to this linearization. Which means that f of x comma y is approximately equal to f of x naught comma y naught plus df dx times x minus x naught plus df dy times y minus y naught. This is what differentiability is telling us. If a function is differentiable, then when you get very close to a point, the value of the function is approximately equal to the value of the linearization at a point. And this idea holds for any functions of any number of variables. So we'll see how to use this in examples a little bit later on. I definitely do want to just write down, though, what happens for the linearization for a function of 3 variables or any more number of variables. Let's say you have a function g of x, y, and z. Okay, then the linearization for a function of 3 variables is going to be found in the exact same way. It's equal to the function, we'll say the linearization at the point r naught in 3D, which is x naught, y naught, z naught. It's the value of the function at x naught, y naught, z naught plus df dx at this point r naught times x minus x naught plus df dy at the point r naught times y minus y naught plus df dz at the point r naught times z minus z naught. So you can hopefully see how this would be extended to a function of any number of variables. The linearization or linear approximation of a function extends for any number of variable functions. And so if we want to extend this even further to functions of any number of variables, 4 variables, 5 variables, up to any number of variables you want to consider, we can go ahead and do this. So consider, say, h, where h is a function of x1 to xn. Or more concisely, where h is a function of position r in some n-dimensional Euclidean space. So we'll say that r here is the vector x1, x2, all the way to xn. And we'll consider the linearization around some fixed point r0, the linearization of the function h around some fixed point r0. So it'll be x1 naught, x2 naught, so on and so forth, all the way to xn naught. And we'll use the formulas from 2D and 3D to sort of guide us along. If you look at the linearization formula in 2D, a little bit of thought and knowledge of what's called the dot product, the vector dot product, will allow you to realize that this is really just the same thing as function evaluated at the point r0 plus the vector dot product of the gradient at the point r0 with this dot here means the vector dot product. So it's the dot product of this gradient vector at r0 with the vector x minus x0, y minus y0. And so a very compact notation for this is that the linearization of a function at a point r0 in 2D is in fact equal to the value of the function at the point r0 plus the gradient vector of the function at r0, vector dot product with the vector r minus r0. Likewise, in 3D, this linearization can be written as the function g at the point r0 plus the gradient vector at the point r0, vector dot product in 3D with the vector x minus x0, y minus y0, z minus z0, or most compactly as g of r0 plus the gradient vector of g. Oops, and I'm really sorry, I just realized that when I wrote this down I was using f here because I forgot that I'm using g for my function of 3 variables. So this should be dg dx, dg dy, and dg dz. Same thing right here. I apologize for that typo. So the linearization of this function g is going to be the value of the function at the point r0 plus the vector dot product of the gradient of g at the point r0 with the vector r minus r0. So you'll see this formula right here is the same formula as the previous formula that we got in 2D, meaning that the idea here is that we can really extend this idea of linearization to a function of any number of variables. We say that it's the value of the function, in this case h, at the point r0 in n-dimensional space, plus the gradient of h at the point r0, vector dot product with the vector r minus r0. So this is really cool. And just in case you don't remember the dot product, I wanted to give a little bit of a review right here. So remember that the dot product is a special product that we can define between vectors. And in 2D, if you have a vector A, which is A1, A2, and a vector B, which is B1, B2, see that the dot product of A and B is equal to the multiplication of the components of the vector added together, component-wise. So likewise, in 3D, where you have 3 components to your vectors, the dot product is going to be the same thing, just with the addition of the third component-wise multiplication of the components multiplied together. So this is something that can directly be defined in n-dimensional Euclidean space. If, for example, your vector, say, is A1, A2, all the way to AN, your vector B is B1, B2, all the way to Bn, then A dot B is again just going to be the component-wise multiplication of all of the components added together, all the way up to AN, Bn. So this is what we're doing here when I'm expressing these as the dot product. I'm basically taking the fact that df dx is the first component of the gradient vector and multiplied by x minus x naught, plus the second component of the gradient vector multiplied by y minus y naught in 2D, just the gradient vector dot product with r minus r naught. Same thing for this 3-dimensional equation, and you can very clearly see that this is going to hold in general in n-dimensional space. Now, a useful tool for us is within this realm of the dot product, the inner product as it's sometimes called, is the fact that this is always going to be equal to the length of the vector A times the length of the vector B times cosine of the angle theta, where theta is the angle between A and B. So in 2D this is going to look like the following. If you have a vector A and a vector B, you can define the angle between them. We know that this length is going to be the length of B. This length is going to be the length of A. This identity right here can be proved in general using what's called the law of cosines. And typically this is done in the Calc 3 course. But what's really neat is that it doesn't take much effort to show that this also holds in 3D and really in any number of dimensions for Euclidean space. So it's definitely possible to visualize in 3D. It's not so easy to visualize in n-dimensional space, but this will always hold, which is very neat. And it's going to be super important when we start talking about the directional derivative. It turns out that this, it's called so the equation on the left here, sometimes called the geometric version of the dot product. This is sometimes the fundamental way that we're going to actually have to go through and evaluate the directional derivative for higher dimensional functions. But it's important that you know this equality and why this equality holds, which is why it's typically covered in a Calculus 3 course. So let's take a look and see what this linearization is telling us about one of the functions that we've been considering. So we'll take a look at the function h of xy is equal to x times y times e to the negative x squared plus y squared that we considered before, because we've already done the calculations out for the partial derivatives of this function at the point -1, -3/2. So let's go through and find the linearization first, and then kind of visualize a little bit what this is telling us about our function. So a linearization L of xy from our previous formula that we got for the linearization is going to be the function itself at -1, -3/2 plus the x partial derivative of this function at -1, -3/2 times x minus x naught, which is x minus -1, plus the y partial derivative at the point -1, -3/2 times y minus -3/2. So we have all of these values. We computed all these values before. This is just going to be the function itself at the point -1, -3/2 is going to be this 3/2 e to the -13/4. The x partial derivative at this point found to be 3/2 e to the -13/4 as well. Remember, so this value right here is just the value of the function itself at -1, -3/2. So we're just plugging -1 for x and -3/2 into this function. That's where this value is coming from. This value is coming from our previous calculation, which we showed the x partial derivative at -1, -3/2 is also 3/2 e to the -13/4. And then lastly, we found that the y partial derivative at this point is 7/2 e to the -13/4. This is going to be times y minus -3/2, y minus y naught, which is y plus 3/2. So this gives us the following equation for a tangent plane, which linearization is really in some sense the same thing as the tangent plane of a function of two variables. And we showed this plot before of the tangent plane. So let's zoom in on this linearization region and see how the function behavior compares to the linearization behavior. So we're going to zoom in this box right here. The domain for our tangent plane is for x minus x naught and y minus y naught, both less than 0.6. So this is what this looks like, kind of zoomed in. You see that as we stray kind of far away from the point in our linearization region, the linearization becomes not such a good approximation of the function. the level curves of the linearization are straying very far away from the level curves of the actual function itself. However, if we stay close to our point, as we expect, right, the level curves of the linearization directly correspond to the value of the level curves of the function, which is the idea with what's called a linear approximation. The closer you get, the closer you expect the linear approximation of your function to match up with the actual function values itself. So let's zoom in by a factor of 10 here, and we'll kind of consider when x minus x naught and y minus y naught are less than 0.06. So this is going to give us a much smaller tangent plane, which is visualized on the left here. And also our linearization region is much smaller. Circled it here in the plot so that you can see it, but it's a much smaller region. And if we zoom into this region and look, we can very clearly see, right, that this tangent plane, or the tangent approximation of our multivariable function, is actually doing much, much better throughout the entire region right here. Because the contour lines, or I should say the contour curves of our tangent plane, which are just lines because it's a plane, are directly matching up with the level curves, which are nonlinear curves of our function. So this is a really neat example, right, showing exactly what we're doing when we do a linearization of a function of two variables. And what's neat is that this, as I showed before, extends directly to functions of 3 variables, 4 variables, like any number of variables, and it's super important in applications. All of the functions in example 1, example 2, and example 3 that I showed are very nice functions. What I want to end with is an example of a function that is not differentiable. This is called the roof function, and its function will use the roof function of 2 variables. It's going to be similar, very, very similar to the absolute value function in the single variable case. So this is, put a warning first. Existence of partial derivatives does not guarantee differentiability. So just because you can calculate the partial derivatives at a point doesn't mean that the function's differentiable there. This roof function is a great example. So the roof function is f of xy is equal to the following. It's the absolute value of x minus y minus the absolute value of x minus the absolute value of y. And it's relatively straightforward to go through and show, using the limit definition of the derivative, that the partial derivatives of this function exist at the point r0, which will just take the origin for simplicity. So we know that partial f partial x at the point r0 is going to be the limit as delta x goes to 0 of f of x naught plus delta x, in this case 0 plus delta x comma 0, because x naught and y naught are both 0, minus f of x naught comma y naught, which is f of 0, 0. Divided by delta x. So f of delta x comma 0 is going to be we plug delta x in for x here and 0 in for y, which will be the absolute value of delta x minus the absolute value of delta x. And f of 0 comma 0 is just going to be equal to 0. This expression will be the limit delta x goes to 0 of f of delta x comma 0, which is the absolute value of delta x minus the absolute value of delta x minus 0 over delta x and this expression will always be 0 because delta x minus itself will always be 0, so this limit is just going to be 0. And you can very easily go through and show the same thing for df dy as well. So for this roof function, df dx at the point exists, and it's actually equal to df dy at the point r0. Both partial derivatives exist and are equal to 0. Despite this, the function is not differentiable at this point, and the linearization is actually very bad at this point. And to see this, we'll do a plot of this function to show, in fact, that this function is not differentiable at the origin. So if we open up a plot here of this function, we can see why it's called the roof function. If I kind of rotate it, you can see very clearly that this function is a continuous function. There's no discontinuities. Not only that, the function is differentiable at several different points inside the origin, but it's definitely not going to be differentiable near these cusp points, which is, we expect these to kind of occur because of the absolute value. And you see it's kind of like a roof right here, where we have a cusp along x and a cusp along y, along both axes. We also have a cusp along y equals x and y equals negative x, so this right here as well. And you can see that cusp very clearly if you look at just the contour plot by itself. But at none of these points along the cusps is the function differentiable, even though it's a continuous function. And you can see why right here. I plotted the tangent plane that we should get at the origin, point 0, 0. And you can see very clearly that the linearization at this point is not a good linearization. It's not a good approximation of the function around points that are close to 0, 0. And not only that, it's never going to be a good linear approximation, no matter how small you make this tangent plane, or how small you make this the rectangle down here in the domain space. We're always going to have this problem. So this is a really good example of a function whose partial derivatives do exist at a point, yet the function is just not differentiable at that point. So just like in 1D, like cusp points are points where a function is not differentiable, even in the multivariable case for multivariable functions. But this is going to conclude the lecture today. Thank you very much for tuning in. I hope you learned something and that you had a great day.